Hey everyone, welcome to this explainer. Look, if you are gearing up for the DPE 803 exam, you are exactly where you need to be. Today, we're diving into a high-energy, totally focused review of your foundational science essentials. We're going to seamlessly bridge the gap between mathematical logic and physical chemical realities. Basically, this explainer is designed to rapidly refresh your memory, lock in that understanding, and give you that absolute edge for your exam prep. Let's get right into it.
To make the most of our time, we're using a quick crash course structure. Here is our roadmap. First, fundamentals of trigonometry. Then, experimental techniques, followed by atomic theory and ions. Fourth, mass spectroscopy. And finally, ideal gas calculations. All right, let's jump in.
Section 1. Fundamentals of trigonometry. Specifically, mastering angle conversions. Okay, so when you're staring down an exam question and need to convert degrees to radians under pressure, you absolutely need a foolproof method. No cognitive overload, right? It literally breaks down into 3 simple steps. Step 1, you start with your given degree value. Step 2, multiply that exact value by pi over 180. And step 3, just reduce and simplify the fraction to get your final radian measure. That's the whole shebang. All right, let's put that active recall to work right now. What is 120 degrees in radians? Take just a second and mentally apply those 3 steps we just talked about. And here we go. This really perfectly illustrates how straightforward the rule is in practice. You take your 120, multiply it by pi over 180. Now the 120 and 180 simplify super nicely. Just divide both by 60, and boom, you effortlessly arrive at your answer, 2 pi over 3. But you know the DPE 803 exam isn't going to just let you go in one direction, right? We've got to keep our minds flexible. So let's completely flip the script. How do you go backward? Here's your task. Convert 3 pi over 4 radians back into degrees. Well, the really crucial point here is that to reverse the process, you just reverse the multiplier. It's that simple. Instead of pi over 180, we multiply our radian value by 180 over pi. Notice how those pi values just cancel each other out perfectly? It's so satisfying. Then you just multiply 3 by 180, divide by 4, and that gives you exactly 135 degrees. Just simple, clean mathematical logic. Moving right along to sections 2 and 3, chemistry basics. We'll be exploring experimental techniques and atomic theory. All right, we're shifting gears out of pure math now and stepping into the physical world of chemistry. And you know, what bridges these 2 worlds perfectly is John Dalton's atomic theory, which actually historically transitioned chemistry from just a qualitative guessing game into an exact mathematical science. Now, in modern industrial and nuclear facilities, chemical tracking is all about precision. But before we can measure anything, we have to isolate it. So here's your absolute foundational checklist for separation techniques: filtration, crystallization, sublimation, solvent extraction, and chromatography. Definitely memorize this list, guys. These are the physical mechanisms used to purify the exact substances we're about to measure. Okay, so once we have a pure substance, we need to know what it's actually made of. Let's nail down these fundamental entities. First up, the atom. An atom is literally the absolute smallest particle of an element that can take part in a chemical reaction. But, and this is a massive caveat for the exam, so listen up, an atom may or may not exist independently. For example, noble gases, they chill out completely independently. But oxygen or hydrogen atoms? No way. They almost always bond. Now, what's really interesting here is the contrast. While an atom is all about chemical reactions, a molecule is defined by its stability. It is the smallest particle of a pure substance, whether that happens to be an element like O2 or a compound like water, H2O, that actually has independent existence. But as we know, things don't always stay stable, right? Especially in super high-energy environments. When a molecule gets blasted by high-energy electron beams, X-rays, or alpha particles, it gets violently disrupted. It'll lose or gain an electron, and that spawns the creation of a very short-lived entity known as a molecular ion. Now, here is a classic exam trap, so please pay super close attention to this one. You absolutely must strictly differentiate between a molecular ion and a radical. On the one hand, a molecular ion has an overall charge parameter. Think something like CH4+. Oh, and quick tip, cationic or positively charged molecular ions are way more abundant. On the other hand, we have a radical. A radical is totally uncharged. Its defining feature is simply that it possesses an unpaired valence electron. Don't mix those two up. Section 4. Mass spectrometry. Measuring the invisible. So we have our ions, but how do scientists actually track and measure these incredibly tiny, short-lived particles? Well, look at this staggering number, 1.9926 times 10 to the negative 23 grams. That is the actual weight of a single carbon-12 atom. I mean, individual atomic masses are just so impossibly tiny and frustrating to work with practically. Because of that, scientists implemented a relative scale. The relative atomic mass scale compares any atom's mass to exactly 1/12 the mass of this carbon-12 atom. It sets our baseline perfectly at 12.0000 AMU. All right, time for an advanced exam-level flashcard scenario for you to really chew on. In an ultra-precise mass spectrometer, what physical parameter adjustment forces a heavier isotope ion beam into a smaller radius of curvature? Think carefully about how magnetic and electric fields manipulate charged particles flying through a vacuum. Regardless of the exact path those ions take, they eventually have to be counted, and this perfectly illustrates the core mechanism of detection. As the separated ions land, an electrometer actually counts the arriving charges. This creates an operational ionic current, and here's the key. That current is directly proportional to the isotopic abundance of the sample. Simply put, more current equals a higher abundance of that specific isotope.
And finally, Section 5, Ideal Gas Calculations, putting it all together.
Okay, let's recap. We've converted angles, purified substances, ionized molecules, and measured their incredibly tiny mass. Now, let's tie all this analytical tracking together in our final module, uniting particle counts, moles, and spatial volume. Here is your ultimate exam scenario. Let's say you have an ideal gas system and it contains exactly 3.011 times 10 to the 23rd molecules of a pure gas. It's maintained at exactly 273.15 Kelvin and 1.000 atmosphere pressure. What is the calculated absolute volume of this system? Let's logically deconstruct the math together step by step. Step 1 is dealing with that massive particle count using Avogadro's number. We take our 3.011 times 10 to the 23rd molecules and simply divide it by Avogadro's constant, which is 6.022 times 10 to the 23rd. That perfectly and cleanly simplifies down to exactly 0.500 moles. Nice, right? Step 2, because we are at standard temperature and pressure, indicated by that 273.15 Kelvin and 1 atmosphere, we can go ahead and use standard molar volume. We just multiply our half mole by 22.414 decimeters cubed per mole. Bringing it all together, you can just logically trace the calculations right down the board here. We go from our initial massive particle count and cleanly translate that into exactly half a mole. And then, under those standard temperature and pressure conditions, that gives us a final, perfectly precise volume of 11.207 cubic decimeters. As we wrap up this explainer, I really want to leave you with something provocative to think about. Today, we've jumped all the way from purely theoretical, mathematical angle conversions right down to the tangible, physical volume of a gas under standard pressure. So what does this all mean? How do these absolute laws, the incredible fact that mathematical logic perfectly maps onto real chemical realities, how does that shape the physical world you interact with and measure every single day? It's kind of mind-blowing when you really think about it. Keep that structural connection front and center as you absolutely ace your DPE EP 803 exam. Keep studying hard, and I'll see you in the next explainer.